We are in Unit 9. This is notes number 7 here. And today we are doing improper integrals. So we have come to the end of this really super important Unit 9, all on integration. We've done so much. We reviewed all of our old stuff, integration by parts, partial fractions, powers of trig functions, trig substitution. Yesterday we did L'Hopital's rules so that we could do what we're doing today, improper integrals. So let's take a look at improper integrals. All right, integrals such as the integral from some number to infinity of a function dx, or negative infinity to a number of some function dx, and negative infinity to infinity f of x dx are types of, they're not the only ones, but they're types of improper integrals. We try to evaluate improper integrals using limits, though sometimes an improper integral will diverge. Diverge means goes to infinity. All right? So remember that each of these represents the area under a curve, doesn't it? So this, in example 1 here, this integral from 1 to infinity represents the area between under the curve, so under the curve 1 over x, from x equals 1 to x equals infinity. So look at that here. I have the graph there for you. So there's x equals 1. So it's this area right here. That area right there. Will this curve ever hit the x-axis? No, it will not. It will never hit the x-axis. So it appears that this area is infinite. It appears that this would always, this type of thing would always diverge or go to infinity. But it doesn't always. All right? Let's work this out using what we know. All right? Now, here's what we're going to do. We're going to, let me get a different color here. We are going to go ahead and find the antiderivative. Find the antiderivative. So the antiderivative of 1 over x dx is natural log x. That's just natural. I'm leaving a space here. Natural log x, absolute value x, right? Now we are going to evaluate from, now, boundaries. I'm imposing boundaries on our boundaries because your boundaries can only ever be numbers. You can never put something here that is not a number, all right? And you can never put a number here, a value here, that makes your function undefined, all right? For instance, I could never put a 0 here because that would make our function undefined. Okay? So, the bottom boundary is 1, and that's fine. I can definitely have that. But the top boundary, I do not want to put infinity there because infinity is not a number. What I'm going to do is I'm going to put b there, and I'm going to let b go to infinity. All right? That's legal. This is legal. But don't put infinity there because that's not legal. All right? That's how I want you to think of it. Okay. Now let's plug in infinity for x. If we plug in infinity for x, or I'm sorry, plug in b for x, and then let b go to infinity. Plug in b for x, let b go to infinity. Natural log of something going to infinity is infinity. Right? Now plug in 1 for x, and 1 for x will be 0. I don't want to say that that's equal to, so I'm going to get rid of my equal to sign. Because what did this do? Infinity minus 0 is infinity. So this diverged, or diverges, okay? Diverge means it goes to infinity. All right? Let's take a look at this one. So this had an infinite area underneath it. Let's take a look at this one. This one looks a little similar. E to the negative x from 1 to infinity. So again, it looks a little bit similar, right? This curve will never hit the x-axis, so just like this curve never hit the x-axis, maybe this diverges as well, or maybe it doesn't. Maybe this one is different. We're going to find out. Okay, first find the antiderivative. What's the antiderivative of e to the negative x? And that is negative e to the negative x. And now we put our boundaries down. 1 to b, where b goes to infinity. Okay? 1 to b, where b goes to infinity. Now before I plug that in, because negative e to the negative infinity, it sounds awkward. Every time you have an e or a number to a negative exponent, go ahead and change that, you guys. Trust me, it will help almost all of us. Alright? This negative, if you wanted to, this negative could come all the way outside your limit. Alright? It definitely could. Could come all the way outside your limit. I'm just going to leave it inside because it doesn't bother me, but if you like, you can totally move that to the front. Okay? Alright, so now put b in for x and let b go to infinity. B in for x, let b go to infinity. The bottom is going to infinity. 1 over infinity is going to 0. So this whole thing is going to 0. Minus, now put 1 in for x. Minus a negative 1 over e, right? So this is 1 over e. So this area is 1 over e. Not only is it not infinity, e is about 2.7, right? This is less than a half, even. FYI. I shouldn't have put that in my blue. I should have put that in my orange. This is less than a half. So not only is it not infinite, it's not even very, very big. Okay? The way I like to think of this is, this curve is getting super close to the x-axis super fast. This curve is getting close to the x-axis. It looks like it's getting close pretty fast, but obviously not fast enough, because it was not fast enough to converge. It diverged. Okay? Example 3. Here's our graph. Here's our function. It's the integral from negative infinity to infinity. So this time, our area is all of this. Right? All of that. So let's figure out, does it diverge or is it a number? I don't know. Let's find out. Okay, first of all, what's the antiderivative? Antiderivative. This is an arctan. This is an arctan because it's an arctan form. The 2 I can just bring outside. That's not a problem. The 2 is going to just come outside. This is an arctan, and it's a fairly basic arctan. Remember your arctan form. So this is where u is just x and a is just 2. du is dx. So it's almost a very straightforward arctan. So we're going to have, I'm leaving myself a space because I'm going to have these infinities, right? So I need a limit. This is going to be the 2 times 1 over 2 arctan x over 2. And we want to go from negative infinity to infinity. Well, I can't put either of those as my boundaries. I never want you to put an infinity as a boundary. So I'm going to call the bottom boundary A and the top boundary B, because that's what we do, right? Over here for my limit, you can do this. I'm going to let A go to negative infinity and B go to positive infinity. That's fine to do. Okay? Or you could set up two limits, but you really don't need to do that. Okay? Alright, the 1/2 and the 2 will cancel each other out, so that's nice. Let's start at the top, which is what we do. What is arctan of infinity? Arctan of infinity is pi over 2. Okay? Arctan of something going to infinity, I should say. That's pi over 2. Let's plug in A now and let A go to negative infinity. What is arctan of something close to negative, going to negative infinity? That would be a negative pi over 2. So this is pi over 2 minus a negative pi over 2, which is pi over 2 plus pi over 2, which is pi. That area is pi. How nice is that? That is super sweet. Super sweet. Okay, next up, example 4. Let f of x be e to the negative x, and let R be the region in the first quadrant between the graph of f and the x-axis. I think we should graph this and see what's going on. E to the negative x, that was this curve up here. Okay? And we only want it to be in the first quadrant, so I'm going to just draw this piece. Okay? So it's something a little bit like that. Okay? All right. Find the volume of the solid. So R is the region between the graph and the x-axis. Find the volume of the solid formed when R is revolved around the x-axis. I'm grabbing a little pencil here. So this is our region, and we're going to revolve it around the x-axis. Going to revolve that around the x-axis. Do you see where it's going? Okay, we're supposed to find that volume. We're supposed to find the volume. So do you remember how to find the volume? I hope so. That was back in Unit 7, I believe. And we're only 2 units past that, so surely you remember that. From your axis of revolution to the far side is big R. From your axis of revolution to the close side of your region is your little r. So there's no little r here. Big R is just top minus bottom, so e to the negative x minus 0. So our volume will be the integral from 0 to infinity of pi r squared dx, pi r squared, because the cross section is a circle. Okay? Remember, volume is the integral of area dx always. So in this case, the area is pi r squared. All right. We just need to figure this out. So let's figure it out. The pi, I'm just going to take out, right? I'm just going to take that out. So then I'll have e to the negative 2x dx. Now, the pi is good. I'm going to leave it out. Okay. This integral, I'm going to take the antiderivative. So what's the antiderivative of e to the negative 2x? That would be negative 1/2 e to the negative 2x. Antiderivative. We're taking that from 0 to infinity, but I cannot put infinity on my boundary, so I need to let b go to infinity here. I have another negative exponent, so I'm not going to try to plug in yet. I'm going to write this as In fact, you know what I'm going to do? I'm going to take this negative 1/2 out as well. So this would be a negative pi over 2. And then I just have to worry about the e's. So this will be 1 over e to the 2x. All right, so we have negative pi over 2 times, okay, put b in for x and let b go to infinity. This will be 1 over infinity, so this whole thing is 0, minus, now put 0 in for x, and we get 1 over e to the 0. E to the 0 is 1, right? So this whole thing is pi over 2. So this volume is pi over 2. All right. Next up. If f has an infinite discontinuity, which is another word for a vertical asymptote, at a or at b or at some c in a and b, then this integral is another type of improper integral. So if one of your boundaries is an asymptote, or if there's an asymptote in between your boundaries of a vertical asymptote, then that's another type of improper integral, okay? If the asymptote is inside, in between your boundaries, then you have to split up your integral into 2 pieces, all right? So let's take a look at this example 5. Example 5. All right. So in this example, in the bottom we cannot have a 0, right? X equals 0 is a vertical asymptote here. So we have a vertical asymptote at x equals 0. So we need to sock that away. That's our boundary, right? So that just means when I make a limit, I'm going to need to have that as my limit as a goes to 0, something like that. But we're going to work this out just the same way as we always do. So we're going to have, okay, what's the antiderivative? I'm thinking of this, I'm thinking of that as x to the negative 1/3. So what's the antiderivative? It'll be x to the 2/3 times 3/2, right? Now, I would like to go from 0 to 1. 1 is not a problem. 0 was a problem, though. So I cannot put a 0 here. I need to make that an a and make the limit as a goes to 0. Specifically, a is going to 0 from the positive side, okay? Because we're going from 0 to 1. So it's going to 0 from the positive side. In this case, it won't matter, but sometimes it does. Okay, put 1 in for x, and I get 3/2. Put 0 in for x, and I get 0. So this is just 3/2. Okay? Next up. Another vertical asymptote at x equals 0. Look at your function. Can x be 0? No, x can't be 0. It would make it undefined. So that's a vertical asymptote at x equals 0. So we'll keep that in mind. We just cannot put 0 on a boundary. Okay? I'm thinking of this as x to the negative 3, right? So let's go ahead and find our antiderivative. It'll be x to the add 1, so negative 2, and then we'll need a negative 1/2 out front. Okay? I'd like to go from 0 to 1. The 1 is fine, the 0 is not fine. Make that an a. Limit as a goes to 0, again from the positive side, technically. Now, before I put in numbers, I have this negative exponent again. I advise you to get rid of that negative exponent, all right? Since I'm going to rewrite this anyway, I'm going to move this negative 1/2 outside. So this will be negative 1/2 limit as a goes to 0 from the positive side of 1 over x squared from a to 1. Now let's plug in. 1 goes in for x, we get 1. 0 goes in, a goes in for x, and then a goes to 0. What is this going to? It's going to infinity. So we get infinity, so it's not equal to, this guy diverges. If you get an answer that's of something that's going to infinity, then your answer diverges, which means this area was infinite. This area was just 3/2. Look how similar those two are. One of them went to infinity and one of them went to 1.5. Interesting. Okay, number 7. Number 7 here. The integral from 0 to 27 of this. Okay, I always want to take a look. What makes the denominator 0? 27 does, doesn't it? 27 makes the denominator 0. So we have a vertical asymptote at x equals 27 this time. So this time 27 is the problem. I won't be able to put that as a boundary. Okay? Not a problem. Well, for this one, I think let's do a little u sub. You want to? I think I'll rewrite this. Well, let me just do a u sub. I'm going to come off to the side and do a u sub. U is 27 minus x. What is du? Negative 1 dx, right? So in place of the dx, I'm putting negative du, and then I will have, okay, I'm just rewriting this. Then I will have a negative, right, from the negative du, and I will have u to the negative 1/3 du. What are my boundaries? Do I keep the 0 and 27? No, because remember, those are x's. I need to write u's here. Unless you put x equals 27 and x equals 0, and then you would go back to x's at the end. I'm just going to keep it u's because we don't have to go back to x's then. So the top boundary, if we put 27 in for x, the top boundary is 0. The bottom boundary, 27 minus 0, is 27, like that. And now, since the top is now less than the bottom, I'm going to change it. I'm going to flip those and make it the opposite sign. So we actually went back to 0 to 27 because of what our u is. All right, time for an antiderivative. U to the 2/3 times 3/2 evaluated from 0 to 27, but I can't put 27 in. I need to put a b there and limit as b goes to 27. Why? Because we had a vertical asymptote at 27. So I can't put 27 in there. Actually here, since we did this u sub, actually, you know what? Actually here, since we did the u sub and didn't go back to x's, our u vertical asymptote was at 0, wasn't it? So I should be doing this. A goes to 0, 27 is okay, right? But this also works. Still a limit. I mean, limit is fine. It's just that we could have put 27 right there. Okay. So we're going to have 3/2 times. Put b in for u and let b go to 27. So we'll have the cube root of 27, which is 3. 3 squared is 9. And now put a in for u and let a go to 0. That's just 0. So our answer is 27/2. Nice. Okay, example 8. Okay, in this one, where's our vertical asymptote? We have a vertical asymptote at x equals 1, don't we? We're trying to find the area from 0 to 3. So we're trying to find this area. Do you see the problem? Well, the problem is happening at x equals 1. So immediately, you guys, immediately, before you do anything else, split this integral up into two pieces. 0 to 1, and 1 to 3. If this was an FRQ, you would get a point just for splitting it up. All right? So immediately split it up. Okay? All right. Now we can go ahead and do an antiderivative. So I'm going to leave room because we're going to have a limit. The antiderivative, this is just like a u because the derivative of x minus 1 is just 1, right? So this is just like a u. So we're going to have x minus 1 to the negative 2/3 plus 1 is positive 1/3. So 3 times that. Evaluated from 0 to 1, but I don't want to put 1 in. That was my vertical asymptote. So 0 to b, limit b goes to 1, specifically from the left-hand side, if that matters, plus, I'm going to have another limit. Okay, it's going to be the same antiderivative, but this time 1 was the problem, so I'm going to have a, where a is going to 1, specifically from the right this time, and then our boundary, our top boundary is 3. Okay? So let's think. We're putting in b for x and letting b go to 1. So this will be a 0. So we'll have 3 times 0 minus, now put 0 in for x, negative 1 to the 1/3 is negative 1, times 3 is a negative 3, so that makes that a plus 3 in there. Plus 3 times, 3 goes in for x, and I have 2 to the 1/3, and that is the cube root of 2, or 2 to the 1/3, you can leave it that too. A goes in for x, and a goes to 1, so that's just a 0, like that. Okay, so we got oh, I see what I did. This was a 1 in here. This was a 1 right there. When you put this, when I put 0 in for x, this was negative 1. So I already had the 3 right here. So I can't do it twice. So this is 3 plus 3 cube root of 2. Okay. Last example. Let f of x equals 2 log x, and let R be the unbounded region in the 4th quadrant between the graph of f and the x-axis. Find the area of R. Okay, let's sketch this out, see what's going on. So 2 log x, when x is 1, we'll have 0 still, right? When x is 1, we'll have 0. So this looks like, the graph still looks like that, but I'm only looking at the 4th quadrant, so I only want to look at this piece. So this is the area that I want to find. That's my area I'm looking for. So how do you find area? Well, it's top minus bottom, right? So the area would be the integral from 0 to 1 of y equals 0 minus y equals 2 log x, right? So this will be a negative 2 log x dx. Okay? The negative 2 can come out. And clearly we have a vertical asymptote at x equals 0. So vertical asymptote at x equals 0. So we can't put that as a boundary. So we will keep that in mind. All right. What is the antiderivative of natural log x? It's one I kind of want you to know. X log x minus x plus c, but we don't need the plus c because we have boundaries, right? All right. I want to go from 0 to 1. I cannot put a 0 down there, though, because of the vertical asymptote. So I'm going to put an a there, and I didn't leave myself enough room, so I'm going to come over here. A is going to 0, specifically from the right-hand side. Okay? All right. Next up, I am going to move that negative 2 out. I wanted to move that out to just clean it up. All right. So what do we get here? Let's see. Well, when I put 1 in for x, I get 1 times 0. I get 1 times 0, which is 0, minus 1, so that's a negative 1, right? When I put a in for x and let a go to 0, I get, so this is a minus in here, a goes in for x, and that's going to 0. So this would be a 0 times natural log of something going to 0 from the positive side is negative infinity. Uh-oh. Uh-oh. Minus 0. So that part was okay, right? Well, this is indeterminate. So I can't say it's equal to. I cannot say it's equal to. I can say it's equal to, I'm going to go ahead and put this negative 2 through. So 2, right, plus the limit as x goes to 0 from the positive of our problem spot was x log x. I can say that. All right? So this was our problem spot. I need to use L'Hopital's. So 2 plus, I need to get this, before I use L'Hopital's, I need to get it to be a fraction. Is it okay if I do this? Just move that x to the bottom, like that. And now I can come over here and say, all right, this is negative infinity, this is infinity, so that is a L'Hopital's indeterminate form. So I'm going to use L'Hopital's here. And the derivative of natural log x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Multiply top and bottom by x squared, and we get 2 plus the limit as x approaches 0 from the positive side of negative x. This would, by the way, this would be a 2 times, because this would be, I would have to do that. Not that it'll matter much here, because this is all just 0. So this is just 2. So this area was 2. All right? Okay. So, know this, you guys. This was a bit of a stretch. You're not going to be asked to do this. I wouldn't ask you to do that on a test even. And I've never seen anything like this on AP exam. All right? So this was a stretch, this problem. So don't stress too much about that. But I wanted you guys to see an application of this. And so that was a nice application where we had to use L'Hopital's rule. I have seen problems on here where you had to use L'Hopital's to do a limit. But so I wanted to show you an example of that. All right, go and practice, because practice is how you will be successful at all of these improper integrals. And watch your notation. Watch your notation.